Hi, my name is Megan, and this presentation will be on the pitot system of an airplane. I've divided this presentation into three parts. The first part, we're going to be talking about the pitot system, its components, as well as how it functions. The second part, I'm going to get into the specifics of the pitot system for the seminal PA 44180. And in the third part of this presentation, I'm going to touch on different errors of the pitot system and how to identify those errors and failures and what a pilot can do to adjust for those. This is a very important system in the airplane in terms of being able to read the instruments and understand how the data is being gathered and given to you to keep you safe during operation. So part one, what is the pitot system and how does it function? First, we need to understand the components of the pitot system and how information is collected and displayed. There are two ports. They're both pressure ports. The first is the pitot tube, which is going to measure the dynamic or ram air pressure as the plane is moving through the air. The pitot tube can typically be found near the nose or under the wing of an aircraft. It's positioned in these places so that it will stay away from any wake caused by the airplane or other air pressure that would disturb the reading. As air goes into the pitot tube, it enters a chamber where the pressure is able to build, and then that information is given to the airspeed indicator, which is the only instrument that uses data from the pitot tube. Next up is the static port. The static port measures the ambient air pressure that is around the airplane. The port can typically be found in the boundary layer of the fuselage, but can be found on the head of the pitot tube as well. The fuselage-mounted static source is more susceptible to errors because any changes, damage, or abnormalities to the airframe, such as dents or nicks, could affect the static port air pressure readings. However, for a static port to be mounted on the pitot tube can be a little bit more costly, which is why they are often found on the fuselage. What's really important about the placement of the static port is that it is perpendicular to the flow of air around the airplane so that it doesn't inadvertently read any ram air pressure or any other air pressure around the airplane that could affect its readings. There may also be an alternate static source, which is required for IFR operations. It's important to know where this alternate port is and what conditions may affect it, such as if it's located in the cockpit, how does the air pressure outside and inside the cabin differ? There might be adjustments that the pilot will need to make, or the pilot might need to just be understanding of any variations in output that might come because of using the alternate static source. It's good practice for the pilot to check the operating handbook for any of this information. So looking at the pitot system, there are three instruments connected to it: the vertical speed indicator, the altimeter, and the airspeed indicator. All three rely on the static port for information. And so the way that the static port is feeding information to the altimeter is that it's reading the ambient air pressure changes from the ground as you ascend and descend through the air, and it's interpreting these changes in altitude position and giving the pilot their distance above sea level. The vertical speed indicator, which is measuring the rate of change in ambient air pressure, is giving the pilot information on how quickly they are ascending or descending. Lastly, and this is the only instrument that uses information from the pitot tube, is the airspeed indicator. The airspeed indicator is going to be reading the pressure of the static port as well as the ram pressure from the pitot tube. It's going to use the relationship between these two pressures to interpret the speed at which the airplane is moving through the air. So if more air is coming through the pitot tube, there is higher ram air pressure, it's going to indicate a higher airspeed. And the inverse is also true. The equation given for this is head pressure minus static pressure equals dynamic pressure, or indicated airspeed. It is important to check and monitor the pitot-static system and its components during pre-flight and takeoff to verify proper function. During pre-flight, it's integral that the pilot remove the pitot tube cover and check for any blockages or damage. The pilot should also check the static port is clear and damage-free. As part of the cabin pre-flight, local altimeter settings should be obtained and entered into the airplane's altimeter. Both the airspeed and vertical speed indicator should read 0 prior to engine start. As the plane begins taxiing, there should be no noticeable change in these readings. As takeoff begins, the pilot should be watching their instruments and making it known that airspeed is alive once the instrument starts moving, and run a cross-check between two airspeed instruments if available in the cockpit, and check that they are reading the same airspeed. If they are not, then there's probably an error in your system. The altimeter and vertical speed indicator should pick up and show the change in altitude as the airplane continues through takeoff. Part 2. What is there to know about the pitot-static system of the Seminole PA-44-180? In the Seminole PA-44-180, the static and pitot pressure systems are combined into one pitot head, which is found on the bottom of the left wing of the aircraft. The alternate static source is located below the left side of the instrument panel. When using the alternate static source, the storm windows and cabin vents must be closed, and the cabin heat and defroster must be on. The variance in altimeter error with the static pressure is less than 50 feet unless otherwise placarded inside the airplane. If pitot heat is needed, which can help in situations of heavy rain or ice or other instances when chances of pitot tube ice are anticipated, the switch is located to the right of the throttles. It has its own circuit labeled pitot heat. This should be checked in case it's popped and not functioning during your pre-flight check. Part 3, what are errors and failures to be aware of regarding the pitot-static system? The most common pitot failure is physical damage to the tube itself. Getting knocked or bent will cause incorrect readings. So it's really important when you're doing your pre-flight or around the airplane that you are careful with the pitot tube, that you don't accidentally knock it, and make sure that you really give it a good look during your pre-flight. The second is burnout. It's important to be aware not to use the pitot heat on the ground for extended periods of time, as this can cause damage to the pitot system and give you incorrect readings. The third is leaving that pitot tube cover on and burning and melting the cover into the pitot tube. The plastic can melt, it can get into the system, and that can cause the pitot system failure. Pitot tube icing is also a risk to be aware of. Be aware of icing conditions, know when and how to use that pitot heat option. And also blockages in the pitot tube. If instruments stop reading, there might be a blockage in the pitot system, in the airspeed indicator. So check for any blockages before flight and make sure that the tube is clear and functioning properly. In regards to the static port, if this fails, the pilot could use the relationship between the power settings and the readings on the attitude indicator to figure approximate airspeed so that it can safely navigate the airplane. Thank you for listening to my presentation, and here are my references.